Okay, so if you remember a few weeks ago, I had asked a question to you about the moon. Do you remember the question? About the moon. Ay ile ilgili size bir soru sormuştum. Kurur herhalde şimdi. Now, the question was this. We know that the moon only shows one of its faces to Earth. That is because the moon is rotating around itself, but it is also rotating around the Earth. And these two rotation periods are the same. So if this is the Earth, as moon is rotating around itself, it just rotates in such a way that it is only one of the faces that is towards the Earth. So we can only see that face. Now, in physics, it is almost never we have such coincidences. If you have equality of two quantities, there's always a reason for that. So why is it that the rotation frequency of the moon around its axis is equal to the rotation frequency of the moon around Earth? Now you have enough information to answer this question. Now, think in terms of tides, gelgitler. Think of friction. And think of the work done by friction. So you have like 5 minutes until I prepare my computer and the projector. Okay, in the exam there are 6 questions. One of them is bonus. There is one explanation question, much simpler than this one though. And the other 5 questions is kind of the type of questions we had discussed even in the quizzes. And some of them are very close to the quiz questions that we did during the class. They should be much easier than homework questions. Okay, because of the English or because of other reasons. What we will do is, I will go to each one of the classes. Okay, so let me also show that slide. No. Okay, in LMS side, I just announced who will go to which class. We have the U1, U2, U3. Around 25 students will be in U1, 25 of you in U2, and 100 of you will be here, if everybody shows up. And I will go to each one of these classes and explain the questions, both in English and in Turkish. Of course, first you are supposed to, I will just give you time to read the questions, and then I will go around the classes, then make my explanations. And if there's still something you don't understand, you can ask me. And the assistants, we will have a earlier meeting with the assistants. I will also explain the assistants what the questions are so that we won't have any misunderstanding about the questions. If during the exam you have any questions, you can also ask the assistants about the questions. They will not tell you how to solve the question, but they will explain you what the question means. If you want, both in English and in Turkish. Okay, so any other questions about the exam? Only 6 questions. You will have around 3 hours. Now, the 6 questions, well, I tried to solve them on my own. It took me like 30 minutes to solve all of them. So 3 hours should be much more than enough for you to solve. Well, the general criteria is if the instructor takes, I don't know, such and such minutes, 30 minutes, then the exam should be twice that much. So the exam is now 6 times that much. So you shouldn't worry about the space. Okay, what I do expect though is that you should write clearly. You have unlimited amount of paper you can use. It doesn't have to be fit. The solutions don't need to fit in a page. You can use 10 pages if you like for each one of them. So I don't want you to just write your solutions in the corners at the size of the pages in cryptic letters. Just explain what you are doing clearly. Okay, maybe after the break I will even put the instructions here so that we can discuss the instructions now. You should write clearly. You should explain all your steps. The questions are like 4 or 5. Each question is around 4 subsections. But each one of those subsections are essentially things that you should do in order to solve the problem. Like whenever you have a mechanical problem, you have to first draw the free body diagrams. So the first sub-question is draw the free body diagrams. So that is something that you should already do. And well, you should show your work every step. If you just write an answer, then you don't get any point, even if that is correct. You should explain to me how you got that answer. And if you got the final result wrong, but you did almost everything correct in your intermediate steps, you will get almost a complete credit. It might happen that you have missed a sign somewhere. I will not deduce much points from just a sign mistake somewhere. Of course, you will get the wrong answer, but it's not that important. The units, the vector signs, they are important. You should put them, as I put it on Tuesday. For any missed vector sign, any vector sign that shouldn't be there, any wrong unit, you lose 2 points, independent of how many points the question is. So from your solution to a question, you could lose more than the worth of the question if you are not careful about the signs, the vector signs and the units. Any other questions about the exam? The significant figures, I will not pay that much attention to it. But there is one question about the significant figures. Well, there will be questions about anything, including the things that we will do today. Well, you will need to take the square roots, the square of numbers, divide, multiply the 4 equations of numbers. You will not need to do calculate the trigonometric functions. You don't need a very sophisticated calculator, but even without a calculator, you can solve the questions. But in some questions, a calculator would help. When you are multiplying large numbers rather than just multiplying it by hand, you can use the calculator. Anything else? Then let's come back to this moon question. Any ideas? Tell me. So your friend is saying that the center of mass of the moon is not at its center, but it's a bit shifted. Okay. So the idea is this, if I understood it correctly. So this is the moon. This is the geometric center. But this is the center of mass. And the Earth is somewhere over here. So the gravitational attraction of the Earth makes sure that this point sits over there. So this is one explanation. Any other ideas? Yes. They are not related. Sorry? Now the period of rotation of the moon around itself and the rotation of the Earth around itself, they are not related, they are not equal. But the period of rotation of the moon the period for rotations around its own axis is equal to the period of its rotation around the Earth. So if this is our Earth, if the moon is over here, and so this is the face we can see, when the moon comes here, it rotates by 90 degrees, so we still see the same face. So this is the question, why? Now let me come to this one. Well, a nice try, but let me put it this way. We have the moon. Suppose that at first, when the moon was first formed, it was its rotation period around its own axis was not related to its rotation around the Earth, the period for rotations around the Earth. So if an object is rotating, well, we will discuss rotational motion in a few chapters, but if you take moon, if it's rotating around its own axis, if you just consider each one of these small masses that make the moon, they all have some velocity. If they all have some velocity, the moon, due to its rotation, has a kinetic energy. But that kinetic energy, well, now, assuming that at first the moon was rotating around its axis much faster than it rotates around Earth, then it slowed down and stopped. What happened to that kinetic energy? So that's one thing you should answer in your model. Well, potential energy, we don't yet know what it is. The friction energy doesn't exist. The friction, okay, that is where the friction comes into the game. Because we have seen that if you do some work on an object, that amounts to a change in the kinetic energy. So if when the moon was first formed, it had a larger kinetic energy than it has now, it has slowed down. That means it has lost kinetic energy. If it has lost kinetic energy, something should have done some work on the moon. Assuming that the orbit of the moon is circular, it shows the same phase to the Earth. Well, I will ask you a few more questions. So it is losing kinetic energy. So you are saying that it is losing this kinetic energy because of friction. Well, there are essentially two forces. There is the gravitational force, that is the Earth acts with a gravitational force on the moon. Well, the orbit of the moon is almost like a circle. So the moon is making a uniform circular motion. So does this gravitational force, can it do any work? Can the gravitational pull of Earth on the moon, assuming that the moon is making uniform circular motion, can it do any work? No, it can't. Because? So this is the direction of the force, and this is the displacement, and they are at right angles. Because for uniform circular motion, the acceleration vector is toward the center, whereas the velocity vector is tangent to the circle. They are perpendicular to each other. So force is perpendicular to the velocity. It means force is perpendicular to the displacement at each instant. So that cannot do any work. So we are left with friction. But where does the friction come from? Mm-hmm. Okay, so did anybody understand the answer? Okay. I will just repeat. I mean, I think it's because of the English. Okay, so I will repeat it in Turkish. I think the English was good enough. So, gel git. That is where the tides come into the game. Gel gitler. So what happens is, let me first start with the tides on the surface of the Earth. That is something we are familiar with. If you have ever been to the seaside, you would realize that depending on where the moon is, the water will be high or the water will be low. So what happens is that if this is Earth, there is some water. Let's just assume that it is covered with water. If you put the moon over here, the moon will just pull the Earth to itself. So when you put the moon here, well, the rock cannot really move that much, but the fluid can flow. So the shape of this water shell will be deformed to an ellipsoid. You will have high water on the side close to the moon and high water on the side opposite to the moon. Both of them. You will have high tides in both ends. You get high tides in both ends because if you just, one would just expect that if the moon is here, the earth is there, the first guess would have been, so it will attract the air, the liquid, so this should be the shape of the water. This would be your first guess. This would have been my first guess, right? But the moon is also attracting earth. So within this deformed shape of the liquid, the earth is also shifted a bit towards to the moon. And then you get this shape. The center of mass kind of stays fixed. Well, this is what happens to the liquids. And if the moon is here, you get a deformation in that shape. If the moon is over there, the fluid will be deformed in the other side. So the fluid here will just flow to these parts. And then you will get such a deformation. This is what we experience. We can see with our own eyes. Well, something that we cannot really observe with our own eyes, but which also happens, is that the shape of the earth is also deformed. Not as much as the liquid, because the rock cannot flow, but the shape of the earth is also a bit deformed. So that if this had been the shape of earth without the moon, when the moon is over here, the shape gets slightly deformed, not as much as the liquids, but nevertheless a finite amount. So this will be the shape of the earth when you put the moon over there. But this means various masses inside the moon, they just redistribute themselves, they move relative to each other. Well, if they move relative to each other, then there's friction over there. The friction trying to prevent this relative motion. Well, if you prevent this relative motion, you are losing kinetic energy. Okay, so it will try to prevent this flow of matter in the rocks until the point that this flow of rock, the flow of rock should completely stop. But if for the flow of this rock to be completely stopped, the sun, the moon should just stay at the same side all the time. Or if you look at from the sun's point of view, here is our earth, this is the moon. The moon is deformed due to the presence of the earth over there, due to the gravitational attraction of the earth. If the moon rotates, if the period of rotation of the moon relative to, if the moon shows always the same face to the earth, the deformation is kind of constant. So it was deformed like this, it is rotating, so it is deformed like this. There is no flow of matter inside the moon. If the moon was not rotating at all, for example, if the moon was here fixed, then when it comes here, the matter on these sides will flow inwards, and the matter in these parts will flow outwards. That would create additional friction, but that is not additional friction and hence loss of energy. So instead of doing that, what the moon does is, once it's deformed, it just rotates around its own axis as it rotates around Earth. Ay dönerken şekli deforme. Eğer kendi ekseni etrafında dönme hızıyla dünyanın ekseni etrafındaki dönme hızı eşit olmasaydı sürekli şekli deforme olacaktı. Şu anda böyle duruyorsa, misal şuraya geldiğinde şu eksen eğer böyle olsaydı, önceden böyleydi ayı. Şimdi dünyaya doğru deforme olmuş olması lazım. Şöyle deforme olmuş olması gerekiyordu şu noktada. Ama böyle deforme olabilmesi için şuradaki kütlelerin içeri doğru hareket edip buradaki kütlenin de dışarı doğru hareket etmesi lazım. Kütlelerin birbirine göre hareket ediyorlarsa arada bir sürtünme olacak. Sürtünmeden dolayı da enerji kaybı olacak. Enerji kaybı ne zaman durur? Ne zaman ki ayın kendi ekseni etrafında dönme hızıyla dünyanın ekseni etrafındaki dönme hızı aynı olduğu zaman. Çünkü ondan sonra artık ay dünyanın etrafında dönerken sürekli deforme olmayacak. Well, the rings of Saturn, you see, you have this moon. Moon is being deformed by the gravitational attraction of the Earth. Well, the deformation is mainly because the gravitational pull at this point is much larger than the gravitational pull at this point. So this point is pulled much stronger than this point. Well, but stronger than this point. So you get a slight deformation. If the gravitational field of the Earth was much stronger, like the giant planets, the deformation will be such that the planet will just explode, break into pieces. So because if you are a giant planet and you are very close to the surface, the gravitational pull at this point will be much, much, much stronger than the gravitational pull at that point. It will be just like, think of yourself, somebody just holds your legs and somebody else holds your arms and they pull you at different strength. So you will stretch, no? And eventually you will break. Not a pleasant scene, but that is what will happen. That is what happens to these planets if they are in a very strong gravitational field. So in these giant planets, if a moon happens to get very close to the surface, they cannot remain intact, so they just break. And you end up, they break into very small pieces. Into very small pieces such that the gravitational pull at two different ends of that piece is not that different. So, of course, if you get a planet, if you get a satellite very close at that dangerous region, a large one, it breaks into very small pieces. Each one will be moving at different velocities because when we were discussing satellites in circular orbits, the velocity of the orbit depends on the radial distance from the center. So this mass over here will have a different radial speed than this mass over here. So they will just move at different speeds. So this moon will just break apart and you will end up small masses all around the planet, forming a ring. So that is how we get the rings in these giant planets we have. All of them have rings. Some very thin, some very visible. I don't think we have an explanation for that. Well, one explanation can be just if you just imagine everything started with dust and sand, right? So gas and dust. So this is our cloud of gas. Now, at some point, the gas starts condensing at an intermediate point. So when it starts to condense over here, it just attracts the other gases. So it would probably, once you start such a region, it would, in a short time, collect all the gas in this region, almost all the gas. What remains will be might remain is just bunches of smaller gases. But it will be harder for it to collect all these gases in the farther region. These gases would probably form larger clumps of matter, forming our giant planets. This is kind of a different mechanism, though. I don't know if this is the answer, by the way. This is just my guess. So, any other questions about the moon? What do you mean? Same phase to the Earth. Well, it depends on the satellite, how you design it. I mean, you can put small rockets to change the orientation of the satellite, depending on the purpose of the satellite. I mean, consider if you are building a spy satellite, you wouldn't like it to look at the same point all the time. It should look around, no? So you should just fire your rockets and change its orientation. Or when we see rotational motion, there's also another way of changing the orientation without use of any rockets. Yes. Well, depends. Depends on how old they are, how close they are to their satellite. If you think of Earth, Earth is a satellite of the sun. And Earth is not showing the same face to the sun all the time, because Earth is much further away from the sun. So the tides due to the sun is much smaller. The rotational energy of the Earth, because of its larger mass, is larger. And so there hasn't passed enough time for this phenomena to have happened to Earth. This is called rotational locking. So these two rotational frequencies are locked to each other to equal values. But Earth is slowing down. It is slowing down in a measurable rate. We know how fast it's slowing down because of this phenomena, the same phenomena. I don't think the Earth will be influenced that much. I mean, you mean, suppose, oh, this is the Earth, here is our moon. We are seeing constantly the same face. If a meteor comes and hits the moon at this point, then the moon would start rotating around its axis. So we would be able to see the other face of the moon. Of course, it will then continue slow down until the same phenomena happens. But its effect on the Earth, I don't know. Some claim that if the moon is not there, then the tilt of the axis of the Earth would be straightened up. So we wouldn't have any seasons if the moon disappears. So those are some claims. Well, let's discuss that in more detail when we discuss rotations. That will be more relevant there. Okay, now let's go back to our let's do this example. The question is this. Just imagine we have this mass. It is making rotational motion on the vertical plane, not the horizontal plane. Or let me try this one. So it is doing rotational motion it should be circular motion. Okay, so it is doing this rotational motion, but it fails at some point. Why? Which you stop? Well, let's see. I just leave it from here. It just goes there. Well, that's kind of, we will see, conservation of energy. If I leave it from here, it goes almost to the same height. There's friction doing some work. If I hold it here and push it really hard, I don't exert any force, but still it makes some rotations. Of course, there is air friction, which slows it down, so its speed will be getting lower. But there is a critical velocity at which it makes the full turn, right? And if it goes below that frequency, it cannot make the full turn and it falls down. So if you imagine this thing in a roller coaster, do you know what a roller coaster is? So this is your train. These are the rails, so this train just comes. There's a loop over there. So at this point, you are upside down. So it just makes a full turnaround. Now, if the speed is not that high, like in this example. Now, this example and this roller coaster example are exactly the same thing, by the way. Here I have a string that creates a force pointed toward the center. In this problem, I have the rails. Since it's a circle, the rails exert a force towards the center. The only effect of the string, this thing, is to exert that central force. There I have the central force, here I have the central force. The problems are exactly equal. The same problem in terms of mathematics and physics. Now, just imagine that this is your train, and at the bottom point, it has some initial velocity. If the initial velocity at the bottom part is high enough, it will almost make, okay. If it is high enough, it makes a full turn and you can safely continue your track. If it's not high enough, if it is very low, it just rises a bit. If this velocity is very low, let's just assume that it doesn't have any engine, there is no forces acting on it, there is no friction forces, there is nothing. So you send it with some initial velocity. If this initial velocity is very slow, then we know that it just rises to some height and it comes back. So it will just come here, move a bit up, and then come back down. If the initial velocity is fast enough, then it will make this turn safely. So it will just start from here, safely make a full loop, and then continue with its track. Well, the trouble is, if it doesn't have enough initial speed. So if you just send it with a slower speed, this means that, I don't know, like hundreds of people dead. So you should know how to estimate these speeds. So the one question is this one. The speed is very low. So what is the maximum height that it can reach on the circular track? Now, we had calculated similar problem. This is similar in a sense to the problem of a trajectory. If you remember, we had this mass, we throw it, it had a maximum height. So this is similar to that one, but the problem here is that, first of all, there is one force that we do not know, the normal force. So there's an unknown force. The acceleration is, in that sense, unknown. We don't know the acceleration. If we don't know the acceleration, how can we calculate this thing? The energy, well, we know the kinetic energy and we know the work. Those are the only things we know. Well, we had proven on Tuesday. On Tuesday, we had seen that if we have the only force acting on an object is its mass. Remember, we had this ball, we threw it up, and then we looked at the change in this 1/2 mv squared in 0.1 seconds. And we also calculated the work done on this sphere in that 0.1 seconds. And we saw that these two were equal. So the change in the kinetic energy and the work done on the object, they have to be equal. It gave us this conservation. So this is constant. So this is constant, we know. Well, this kind of it simplifies our lives. It is constant over here, whatever the value over here. It should have the same value over here when it goes to the maximum height. So this is our roller coaster. Let's just assume that this is our z-axis. So that constant, 1/2 mv squared plus mgh, this is our origin. This is nothing but 1/2 mv0 squared. H is 0. Now, how can I use this information to calculate the height? Yes, so when I have this thing, if I move it with a slow velocity, it goes to a maximum point. There it stops and it starts moving back. So at the maximum point, it stops. So speed is 0 plus this should be equal to 1 over 2 m0 squared plus mg, the maximum value of its height. So we can determine h max. One over mg times 1 over 2 m v0 squared. v0 squared over 2g. Do you remember this formula from somewhere? What? Maximum height for a projectile with constant acceleration. Okay, so let me, I don't know if I still have my ball. Yes, this is my ball. This is our trajectory. So let's just assume that I will be throwing at this with the same speed. This is one problem. So this is my height. I throw it with the same speed. Did I reach the same height? Both are projectiles. The heights were different. I mean, one of them went this high. The other one with the same velocity, same speed, it went. Which dimensions? Angle. Who said angle? Okay, so angle is different. So angle has an effect on the maximum height in the projectile. So what is this formula? For which angle does this correspond to if it is the maximum height? So with which angle should I throw it? For 90 degrees. Well, the answer is over there, vertically upwards. So, well, that is kind of weird, no? I mean, if you take this mass, if I throw it vertically upwards, there is the gravity. Well, the change in the kinetic energy. Okay, no, let me put it this way. There is only gravity doing work on it. But in this roller coaster example, there are two forces. One the gravity, the other one is the normal force. The normal? So the normal is perpendicular, so the only force changing the speed, not the velocity, the speed, is the gravitational force. So that's why we have the same answer, because it's only the gravitational force that does work. And the work done by the gravitational force only depends on the height, how much height has changed. So this tells me that if I have some initial velocity v0, this will be the maximum height that it will reach. Well, this is independent of the shape of the roller coaster, whether it is a circle or something else. This will be the same height. Now the next question is this one. So we want the roller coaster to go around the loop. So what is the minimum speed? Yes, tell me. So you are saying that H max is 2R. So V0, at least the minimum V0 should be square root of 4GR. Right? Yes or no? Yes. One right answer over there. No. What is missing here? Suppose I send my mass with this velocity, with this initial speed. What will be its speed when it reaches the top part? But if it is at the top of this roller coaster with 0 speed, what prevents it from falling vertically down? Well, friction just tries to prevent the relative motion of the surfaces. So imagine it like this. There is friction between this chalk and my hand. If I just remove my other hand, it just falls down, because gravity is pulling it down. Well, the only acceleration it has is downward because of gravity. Sorry? Okay, one problem that most of the high school students have is you just look at the numbers. And you don't read the questions usually. You just look at the numbers, so those are the relevant ones to solve the question, and you just proceed to solve it. Very slow speed. So why is it necessary to have a very slow speed? It doesn't reach this 90 degrees. Because if it goes over the 90 degrees, it might not be able to reach this maximum height. So this is the wrong answer. Because if this case, when the cart reaches the top, it will have zero velocity. If it has zero velocity, it just falls down. It will not be able to go around. If you want it to go around, at the top, it should have some velocity, some speed. So that it will, rather than falling down, it will just continue in this direction. Okay, so now you have 10 minutes to think.